Welcome to our webcast, A Structured Approach to the Physical Network, sponsored by Panduit. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering. To get the best results from the Control Engineering webcast platform, please make note of the following as you participate in today's event. First, please make sure that your pop-up blocker is turned off. This is an option in your browser software. If you're having technical problems with audio or the slide presentation, click on the question mark at the top right-hand corner of your screen to bring up a list of system checks to make sure. Look over before escalating to the online technician. If you're experiencing issues with your slides or audio, please refresh your browser or click the Refresh Media button directly under the presenter's headshot. You can control the volume settings of this webcast by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If you need a technician, type a message into the Ask a Question box and someone will get back to you as quickly as possible. Individual technical questions will be answered in the Answered Questions area on the left-hand side of your screen. You can use the Ask a Question box on the left-hand side of your screen to type questions for the speakers during the presentation for the Q&A session at the end. You may ask questions at any time during the presentation. We'll get to as many as time allows. Questions that are for today's presenters will be answered verbally during the Q&A session at the end of the webcast. To download a presentation, copy of the presentation slides, or if you'd like to download a certificate of completion from today's event, use the event resources on the left-hand side of your screen. The webcast is being recorded, including the Q&A session. We'll post the archive on the Control Engineering website in a few days and send you an email message with a link connecting directly to it after it's ready. Today's webcast sponsor is Panduit. Thank you for supporting this program. I'm now happy to introduce today's distinguished speakers. Michael Berg is a Solutions Marketing Manager for Industrial Automation for Panduit Corporation, a global leader in network and electrical infrastructure solutions based in Tinley Park, Illinois. In this position, Michael is responsible for strategic and solutions marketing for the industrial automation market. Michael has responsibility for customer requirements, program strategy, converting technical positioning into key market messages, and ongoing sales support. Michael has been with Panduit for 24 years and has experience ranging from research and development, product management, marketing, and most recently, solutions marketing. He has focused on control panel solutions recently and leads the introduction of Panduit PanelMax offering, which helps organizations reduce cost and risk in control system deployments. Robert Elliott is Senior Product Development Manager for the Copper Group for Panduit, a global leader in electrical and infrastructure solutions based in Tinley Park, Illinois. In this position, Bob is responsible for development of the business case to approve projects and programs that lead to new product introductions. He has responsibility for understanding solutions to customer problems and requirements, defining new product performance, and putting forward to management the recommendations to expend resources to design, develop, and release new products that are in line with the Copper Group's and solution team's goals and objectives. Bob has been with Panduit for 9 years, and prior to that had been employed with leading telecommunications company with experience ranging from engineering design, engineering management, research and development management, and product line management. With the Copper Group, Bob is focused on interactive support of the solutions teams, in particular working with the Industrial Automation Solutions team. Bob has led the development of the business case and project for an industrial-related cabling solution going from the control panel to the machine in industrial automation applications. Again, I'm Mark T. Hosky, webcast moderator and content manager for Control Engineering since 1994. Before we continue, please take a moment to remind yourself about dealing with the technical issues during the presentation. I won't go over them again, but you can just review this slide quickly. And now on with our presentation. First speaker, we'll hear from Mike.
Okay, thank you, Mark, for that introduction. Very glad to be with you. So I'm going to jump right into the agenda. So our presentation today is going to be focused mainly on taking a standards and a structure-based approach to the physical industrial network. So a little bit about what we're going to cover today. So I'm going to spend a little time talking about the business trends and what's driving the growth and the importance of the industrial network. And then Bob Elliott's going to join us as well and talk a little bit about turning that network vision into a game plan for you and discussing things like network assessments and getting more into the standards and the cabling infrastructure for a best practice physical design. So that's a little bit on what we're going to cover today. So let me go transition here. All right, so every organization today is being challenged to transform. And I think one of the things that's most important, a lot of us recognize it, but we may not see it every day, is that the need for business growth and technology are so strongly linked. And this is a trend that's continuing, and it's imperative for the future of manufacturing and of process organizations. So we have a little quote here from McKinsey, and McKinsey is characterizing that for markets like North America and Europe, actually the growth of GDP is only going to come from those companies that are these do-it-smarter type of companies, the ones that can build a better business model and that can reap the benefits of innovation and business agility. So it's very important that productivity and growth of companies is so linked with technology. And kind of to that end, there's a thing that's called the Internet of Things, and it relates to industrial networking. So there's evidence that's all around us that industrial networking and industrial Ethernet is becoming more and more pervasive. So there's estimates that up to 100% of plant floor devices will be providing data as soon as 2018. That's not that long from now. And as the availability of Ethernet-enabled devices increases, what we're also seeing is a number of nodes just explode. So if we even look at the current numbers today, there's 160,000 new industrial Ethernet nodes being added every single working day. And that's growing every day as well. And so what's also happening is that industrial IP networks are becoming more of a network fabric, something that more easily and securely connects vital services. So this idea of this network fabric can better enable a variety of services that industrial relies on. This includes industrial computing and things like the cloud, being able to leverage wireless and video and remote and mobile access, energy management, safety, and security. Being able to leverage all of these things through the network is important to be competitive and build value. And this drive to connect devices and gain value is captured by the concept of the Internet of Things. So the value at stake over the next 10 years with the Internet of Things is calculated at about $3.9 trillion for manufacturing. And how that value is going to be represented for end users is in innovation and efficiencies, employee productivity, asset utilization, and an improved customer experience. So there's also a challenge as well. So not all manufacturers are ready to fully understand how to capitalize on this opportunity. So the point with this slide is that the role of industrial networks is changing, and we need to adapt how we design, install, and maintain these networks so we can reduce our risks and we can reap the value and the opportunity that is represented by the Internet of Things. So I'm kind of transitioning a little bit here as well, and pointing another trend that's happening as well in industry is that industrial networks is really becoming more of a discipline. So standards and methodologies are being leveraged much more in order to build network reliability. So as a case in point example here, we've got some Aberdeen research here that we have up on the slide. And Aberdeen has done some research that helped define a profile of best-in-class manufacturers, as well as the industry average manufacturer and those that lag behind, and kind of did some comparisons between those as well. So their research covers many areas, but the one I'm going to focus in on here relates to the importance of the physical layer of the network to business performance. So what we see revealed in this slide here, where you have the dark blue showing the best in class, and you have the light blue showing all the others, the industry average and those that lag behind, what was revealed is those that are defined as the best in class are putting a greater emphasis on network management, and they're taking greater steps to ensure network reliability and resiliency. So this would include steps that a manufacturer might take, like utilizing redundant devices like switches, routers, and power supplies, building in redundant paths so that a single device or a failure in a link doesn't cause a network to go down, the entire network to go down, and avoiding downtime. And then also understanding the importance of having a cable management and a wiring strategy for the physical design. So this helps ensure that the data speed is maximized throughout the network across the plant floor. So what I also wanted to show you here as well is the criteria that they're using to define best in class. And this is some pretty impressive numbers here. So they've got your best in class is defined as 8 hours of downtime, so 99.1% uptime, 11% total cost of ownership, reduced total cost of ownership, a 90% OEE rating, and then a positive 25% operating margin contribution. So very, very strong contributions there. And the point here with this slide is that the infrastructure is very critical to meeting those performance goals, and that using a good methodology can provide results. So another point we wanted to make for you as well is looking at the percentage spend on different elements in the network, as well as the lifespan of those components. So if we look at the different elements we have listed here, software represents about 60%, networking elements represent about 23%, the electronics side of it, the gear side of it, operations represent about 10%, and the cabling infrastructure, the physical elements here of the infrastructure, only represent about 7% of the network. So IT budgets tend to spend most heavily on software and hardware, obviously from the numbers that we see here. And a very small percentage of that budget is going to be going to the cabling. However, what we also see is that up to 80% of those network problems, when they're troubleshot and the cause is determined, they can actually manifest themselves in the cabling infrastructure itself. And so the tendency tends to be to go after the simplest approach possible, and what that tends to do is cause capital expenditures and equipment replacement, which may be unnecessary. So this is one of the points that we're making here. And the other thing to notice here is the amount of turnover on the equipment. So if we look at the networking, for example, every 5 years is the average of when networking gear would be replaced, and we compare that to our cabling infrastructure, it's lasting for in many cases, 20 years or longer. So it's very possible that the network gear is going to turn over 4 to 5 times through that existing cabling infrastructure. So what the point here is that it pays to be forward-looking when planning the cabling that you're using and the connectors that you're using. So we wanted to show you some examples here from the real world. We all know that this type of thing happens. These types of pictures are always amusing to look at, and it happens to the best of us when we're trying to implement one of these systems. But none of these types of physical designs that are poorly planned, none of them are fun to live with and have to deal with on a day-to-day basis. So the guidance of standards-based approaches in the physical design is critical to avoid these types of situations, avoid the network sprawl, avoid those troubleshooting nightmares and safety and security issues. And to kind of further make this point, why we have a tough time correcting these types of real-world situations that we've all dealt with is that late in the game, when it's already been deployed, it's very expensive to fix these types of issues. So something that may have cost $10 for a single issue or some single design element in the planning stage, at the end stage, in the deployment stage, it may cost $10,000 and a full-blown crisis to fix that out in the field. So we want to avoid those problems in the late stages because those tend to lead to missed deadlines and overtime costs and costs to bring in outside people, travel and expense, and these types of things. So to kind of summarize this section, there's a strong physical network design guided by standards is really important to provide that reliability and reduce risk right from the moment that the logical network is known. So for the rest of the presentation, we're going to switch gears a little bit, and Bob Elliott is going to outline some of the steps that can help turn your network vision into reality. So he's going to give us kind of a primer for the physical design in the industrial network. So he's going to touch on physical design considerations from the logical network requirements and from network assessments. He's going to review a standards-based approach to the physical design and how that relates to the network requirements. And he's going to provide us some starting point elements with the physical design. And with that, I'm going to turn things over to Bob Elliott.
Thank you. Thank you, Mike. And good afternoon, everyone. So first of all, in terms of that structured design approach, what you have to do is to look at some of the basic factors that are going to control and influence your network. Well, how do you make such an assessment? We'll start with the most basic of considerations. Count up all the devices that need to be connected. This could be machines, sensors, controllers, cameras, drives, or switches. You need to plan not only for today, but for the next 10 years. And as Mike said, in those cases where that network cabling infrastructure is going to be lasting for 20 years or so. Then you also have to consider the network, the traffic, the volume, the type, what type of data. For example, video, control information, voice over IP, and look at the time criticality for process control. And this will lead you to understanding the bandwidth requirements, which is going to influence the type of cabling choices that you make. Walk through the plant and envisage how to run the cable. Not only how you run it and where you run it, but in what kind of environment it's going to be located in. Industrial environments are rather special and are different from those encountered, say, in the office or the enterprise. That big difference is that cabling can be subjected to harsh environments, for example, high temperatures, weld splatter, UV, and we'll talk about that a little later. Lastly, work with manufacturing operations to establish an agreed expected network availability. How critical is that network for operations? How much does that downtime cost? This is the point where you begin to balance the downtime costs with the appropriate level of network availability. When deciding on a network topology, you should also consider a degree of separation of redundant media paths. Will you use one backbone or will you use two? If you use two backbones for a main and a redundant, do you use different paths to improve that uptime? Recall the network topologies I showed earlier, like redundant or starting or ring. What level of hardening is needed to withstand your manufacturing environment for the long term? Again, that 20 years. Are you getting the expected network performance? Are you experiencing high levels of errors like bit error rate, frame error rates? You should require contractors to provide network performance data on all those links, verifying their performance and reliability. In this picture, for example, imagine if a network cable was running along the top of that door. What would happen to your plant if you lost the backbone network? One of the starting points for that network design is to consider the logical architecture. Logical architecture will show you the broad network connectivity for different switches, servers, firewalls, and as you can see in this diagram here, the lowest switch there then is distributed in various zones to different endpoints. These might be switches, they might be PLCs, they might be individual nodes. So how critical are these nodes to the process and safety? And of course this is ensured by high performance firewall that effectively separates the manufacturing network from the internet. Who owns this infrastructure? So moving on, we talk now about the standards, some of the resources that can be used to designing structured cabling networks in the industrial premises. Well, perhaps the lead document used for network design has been created by the Telecommunications Industries Association, TR 42.9 Committee, the Industrial Infrastructure Subcommittee, that publishes standards based on infrastructure that give guidance for distances or for cabling, the locations and configurations for the outlets and connectors, and the topology requirements for the cabling. So this kind of standard is an interface between that logical topology we showed just previously and what the actual network looks like in the real shop floor environment. And as such, this standard addresses industrial areas, what happens in those harsh areas. It talks about telecommunications spaces, where you should have racks and cabinets with equipment. It talks about pathways. It talks about fire stopping between walls. It addresses backbone cabling, which is typically cable that rises vertically throughout a building, and horizontal cable, which is then primarily distributed horizontally to work area outlets. It also addresses aspects such as grounding and bonding, and finally gives guidance on industrial cabling performance requirements. So just to show how this standard, TIA 1005 for industrial premises, fits into the bigger picture, these are some of the key applicable industrial telecommunications standards. And they're actually divided into three broad groups, identified in blue, green, and light brown. The first one, a series of standards, are called the common standards, when you can see, first of all, a generic cabling standard that applies basically at fundamental level to all types of premises. Then you would also associate this with that cabling with the pathway standard, the administrative standard. What is that? Well, it addresses layout and labeling, not only of racks and cabinets, but also identification for components like patch panels and structured cabling. If you have a horizontal cable 90 meters long, how do you know at one end of that cable that when you get to the other one, it's the same cable that you wanted it to be? You do that by suitable identification and labeling. Grounding and bonding standards. Outside plant, that is associated with cabling outside of the premise. And then finally, building automation standards. So these generic standards or common standards then move to distinct premise standards. What are the particularities of the industrial environment that would separate it and make it different from, say, a commercial building. And we've already touched on that, of course. One of those differences would be the types of harsh environment that you see in industrial. And finally, each of these premise standards relates to component standards. And we see here two that have been flagged up. 568-C.2 is for balanced twisted pair copper cabling, and 568-C.3 is for optical fiber. So as we drill down one level more, we've talked about the topology used in the industrial network. We've talked about some of the standards. And now we actually see how those standards and that topology map into exactly what a structured cabling system looks like in the industrial automation application. Well, let's start with the definition for structured cabling in the first place. It's a planned cabling system which systematically lays out the wiring and wire management necessary for communications, including voice, data, and video. And here we see an example of a small factory, for example, that includes office-based work areas, but also a work area on the industrial factory floor. Cabling would typically enter the building at what they call the entrance facility, which is identified in number 1 at the bottom left-hand side. From that, you'd expect to see backbone connections to the data center as identified. And also in this diagram, we have another riser cable going vertically to the telecommunications closet at number 2, identified in the diagram. And from the telecommunications closet, access cabling would progress and be routed to the work area. And, for example, that might be used to communicate with desktop workstations. And on the shop floor, of course, we see the riser cable or vertical cable going again to the micro data center, which is located, for example, in the control room. And from there, horizontal cabling connections would be attached to, for example, a zone enclosure, and then from the zone enclosure to the control panel. Here's a diagram that you'll see in this standard TIA 1005. And this is actually shows the architecture for the cabling infrastructure. You'll see that the names that are identified here don't look very much like the ones that we've already talked about. But however, they map directly into the kind of infrastructure that we've shown in previous slides. You can see MC would be, for example, the entrance facility. IC would be, for example, the data center. HC would be the telecommunications room or the micro data center. And that could lead to those optional consolidation points, which might be zone enclosures. And finally, to the telecommunications outlet, which basically would be the last connection to the device to which data is being sent. So let's look at the structured cabling schematic here in the industrial automation area. What's happening here is the work area shows various types of industrial application, the factory floor itself, and then a work area and an automation island. And you'll see on the left-hand side, we've identified here the different types of criteria defined by the term MICE. MICE stands for mechanical, ingress, chemical and climate, and electromagnetic. And we'll talk more about those in a second. But you can see that this shows the different types of areas that you can see in the industrial plant floor. Just expanding on that slightly, some of the different MICE criteria is determined by that number that you see under each of those letters. 1, for example, would be an office environment, 2 might be light industrial, and then 3 would be harsh industrial, perhaps up by that welding machine or in the presence of sort of motor control centers. And you can see there that the term mechanical takes into account sort of shock and vibration, bump. Ingress is concerned with 2 parameters, that is water ingress and ingress of particles. Climate, of course, temperature, humidity, exposure to ultraviolet radiation. Chemical, what kind of caustic chemicals or acidic oxides are in the air or in proximity of the machine or the cabling. And finally, electromagnetic. It could be transient, it could be static discharges or radiated noise. And here we start to see some of the different MICE criteria that you might see on a typical shop floor. And so that when you get to that automation island, you're in a fully encountered MICE level 3 type of environment. Here's an example of that zone enclosure that we talked about. And this is an integrated network zone enclosure, and it's actually provided with some of this equipment already in there to allow you to effectively take, for example, fiber cabling that comes into the top left of that enclosure. Dielectric clad fiber is led in through effective slack management and then led to the network switch. From the network switch here, you'll see the white patch cords, copper patch cords that are used, that go into the patching solution on the right-hand side, again mounted on, that's all 3 devices are mounted onto that DIN rail. So that the patch cords are then inserted into jacks located in that patch panel, and you can see the green cabling is actually coming from the underside of that patch panel and then is managed and goes vertically up and out through the top right-hand conduit. So, for example, this structure would fit in to that topology that we talked about. This, from the telecommunications room, would then communicate, for example, by fiber to the integrated network zone system. And then from the zone system, individual copper links would be routed and led to control panels. So one of the interesting things that we're seeing in the industrial environment is the different cabling types. We've talked so far about standards-based cabling based on TIA standards, based on a zone type of topology that's been advocated by the logical topology that we saw earlier on. So we can see that structured cabling that's often driven by the IT groups is being driven down from the micro data center to the zone system and also to the control panel. However, in the control panel industry, we're also seeing the predominant move of folk to field install cabling, taking stranded cabling and installing plugs onto those, going and then achieving network connectivity. So just to summarize, structured cabling is a solid horizontal cable terminated with jacks, and typically the horizontal cable is installed and then left in place. Patch cords are then used to connect those jacks on the solid cable to the actual equipment itself. We use the term point-to-point cabling as being comprised of stranded cable, field terminated with plugs. The interesting thing here is that measurements are infrequently done. With structured cabling, we mentioned before that it's almost invariably measured and then warranted for performance. And the measurements are taken and often left with the end user and can be referenced in the future. Whereas with point-to-point cabling, we've often found that, first of all, there is no standard so far to define the test method. However, we do know that that is being worked on in the standards groups. And some of the areas we've seen is folk will field install and then connect up, and if the green light goes on, that means it works. So just to talk about structured cabling for a second, we've talked about the horizontal cable. The RJ45 jack is very prevalent in that area. The horizontal cable, tested, and then use patch cords to connect to equipment. We see this diagram of how structured cabling can be used here to go from the control room or the micro data center through possibly a zone enclosure and then to the control panel and cabinets. And you can see some of the equipment here. The patch panel on the top right would be input with, for example, horizontal cable. Patch cords would lead from that horizontal cable to a network switch, and from the switch would control other devices like the programmable logic controller or the variable frequency drive. Point-to-point cabling, we've talked about stranded cable terminated with plugs. It's often used for flexibility, so it's more subject to movement. Solid cable itself is a little bit more prone to breaking, and that's why it tends to just be left in place. The other point about stranded cable is the stranded cabling attenuation is higher than that of solid cable, so you have to take that into account, and what it means is it has to be derated for a length. And the testing can be especially difficult, and here is the concern why testing is so important. One of the things that Mike talked about was the increasing data rate, so that if you install cable now and it's not tested, you don't know, for example, 5-10 years down the road, whether it's going to be suitable for that higher data rate piece of equipment that you install. So Panduit would always advocate structured cabling, but we understand there are situations where you might want to use point-to-point cabling, and we're just trying to show those considerations. Some of the areas where you would use structured cabling is if you wanted to understand the performance of it, and in understanding that performance, you're then in a better position to future-proof and understand what will happen when you replace equipment. Point-to-point cabling, for example, could be used if you're pulling cable through a conduit, and you don't want reels of slack cable coiled up and left on the base of a control panel or an enclosure, and so to be able to cut that length of cable exactly to length can be advantageous. Finally then, as we look at a facility assessment for cabling, some of the devices that areas that we've talked about, the considerations, connectivity count, the number of devices. That impacts the number of cable runs, the pathway sizes, the number of ports, the idea of future-proofing. Do you just install the number of horizontal cables that you need, or do you actually install more of them and just blank off those exposed jacks so that you can use that horizontal cabling later? What type of environment? We've talked about the MICE criterion. What kind of bandwidths? Again, that future-proofing where you know the performance and it can accommodate higher data rates. The standards will give you information about the cable reach. The copper cable, the classical TIA channel is based around use of 4 connectors and a 100-meter channel, which typically comprises up to 2 5-meter long patch cords and 90 meters of horizontal cable. What about safety? What about proximity to devices such as fluorescent lights, generators, arc welding machines, for example? What about security? Who gets access to the cabling? And then, of course, the longevity, the years of service that cabling might be expected to endure. The availability criterion or considerations, that we've also talked about: redundancy and separation, hardening, the connection type, point-to-point or structured cabling, troubleshooting, what kind of devices or aspects can kind of help us there. And then finally, to promote the reliability and the uptime of the network that Mike talked about, what kind of mistake can we avoid and protections can we put into place? Finally, the media selection that we talked about. Copper cabling, 2 types of fiber, both multi-mode and single mode. These will allow you to reach different lengths experienced in the shop floor environment. What kind of noise areas are you seeing? The idea that if there is a radiated noise or conducted noise, the idea of using shielded cable versus unshielded twisted pair cabling. Of course, fiber has the advantage that it's noise immune. The bandwidth requirements that you require. These are often, for copper, limited to gigabit, particularly on the shop floor, higher than that, though, in, for example, the data center, whereas multi-mode and single-mode fiber would be used for 10 gigabits. What type of bundles of cables would you see? And finally, is that medium capable of power over Ethernet? Choose your connectors wisely. This diagram here is rather difficult to understand, but what it shows is the kind of performance criteria that are considered in those component standards, the 568 C.2 and C.3 we mentioned, and various parameters are talked about here. Insertion loss, of course, is a measurement of the attenuation of that cable. And then next, nearing crosstalk shows how much energy is going from one pair within the cable to another pair. Other considerations that you might need to consider, obviously the cable, the bend radius control, that's critical in the installation. That always has to be looked at. The bundling of cables, how they're routed within pathways. What type of pathways are you going to use? Ladder rack, wire grid, is it overhead, is it underfloor, is it suspended in J-hooks or rated in conduit, so it's protected and out of harm's way. Labeling, the use of color coding to assist labeling and infrastructure identification. Labels, bands, colored cables and jacks can always be used to facilitate that. And finally, don't forget grounding and bonding. It's critical not only for communications, but also safety, of course. So these are just some of the considerations here, and I'd like to just hand it back to Mike for just a brief wrap-up.
So thank you, Bob. So as we move towards concluding the presentation, I'd like to cover what we'd like you to take away from today. We hope that we've shown you some of the importance of evaluating and assessing your current network and the needs that relate to the physical design. We also hope that we've given you a good primer and a start of an understanding of the standards that are relevant in the physical design and some of those elements that are critical in the infrastructure to get you started on planning. And we've tried to show you throughout the presentation how the structured approach to industrial networks can help you improve your performance, reliability, and extend the life of your network. So lastly, what I'd like to offer as well is that Panduit has the capability to help you in these network assessments and in the design process as well. We have this capability through Panduit advisory services as well as through our integrator partner companies. So I just want to note that as well if there is a situation that you need some help on. And going to the final slide, just wanted to review for you as well. We kind of did a primer today in reviewing the physical network infrastructure. There's certainly a lot more that we could talk about with this topic. So if you would like to dive deeper on the physical design, there are many references and different guides that we have available that we can provide to you. We have reference architectures available that support the physical design. White papers and articles can help you with some of the guidance, and also elements of design as well. Design guidance and tools are available as well. I wanted to make note as well, I made references earlier to the Internet of Things and some of those business trends. If you are out there doing research from the business perspective and kind of the forward-looking perspective, we'd like to encourage you to go out and check out the Industrial IP Advantage community. It's www.industrial-ip.org. This is both an educational and a community site, and it has the latest in content on open standard industrial networks. And finally, I wanted to say, kind of to support this presentation and this concept of structured networks for industrial, Panduit is going to be launching a landing page on our website around the topic of structured industrial networks, and we'll be posting a technology brief that follows this webinar outline. So we'll be posting that after this presentation. And so that concludes our presentation. I'm going to turn it back over to Mark and see if we have any questions.
Thanks, Mike. Thank Bob. It was a great presentation. That was an excellent resource slide, and if anybody was listening and couldn't take notes quickly enough to get all of those, you can certainly use the download function to download the presentation. Please stay with us, because the Q&A is oftentimes the part of the most interesting area of the presentation, and we'll get on to that right now. So to submit our questions, type them in for today's presenters in the Ask a Question box on your screen. We'll get to as many questions as we can before the top of the hour. Questions will be answered verbally during the Q&A session, and within a few days the presentation will be available for on-demand viewing. We'll post the archive on the Control Engineering website and send you an email message with a link connecting directly to it after it's ready. And now on to the questions. So let's see. Can you clarify what you mean by the term future-proof when designing a structured approach to the physical network?
Well, that's a great question. There's several things that can be considered. The first one is the idea of when you're looking at that design of that topology, first of all, how many endpoints or devices do you think you're going to need to be connecting? Then the idea of what kind of lifetime do you expect the cabling to last, and how many equipment refreshes, as Mike mentioned, do you expect to find? So the idea is to plan for the future rather than to plan for the present. The second thing, of course, is to consider the rising data rates. 10 megabits or 100 megabit per second is very common with Ethernet IP on the shop floor. But as we transition to higher data rates, the next logical step is going to be gigabit signaling or data communications. So that's a factor of 10 higher data rate. Will the cable that you install today be capable of that data rate tomorrow?
Good. Could you say just a little bit more about the data rate versus cable types?
Yes, great question. When Ethernet copper cabling first started to come into the industry in the late 1980s, data rates were considered to be, sort of 10 megabits per second was extremely fast. The fundamental data communication standards were developed by the IEEE, the Institute of Electrical and Electronic Engineers. And their philosophy was to say, to make a meaningful standard, I'm not just going to double the data rate, I'm going to make it increase by a factor of 10. So in those days, the next step from 10 megabits per second was 100 megabits per second. And of course, the attendant copper cabling performance had to improve to support those data rates. And optical fiber technology, of course, came to the fore with the development of both multi-mode and single-mode fiber capable of supporting those higher data rates.
Very good. A question about patch cords versus a cable assembled point-to-point link. Why would you use one versus the other? In what situation?
Yes, great question. The interesting thing is, of course, is that the field-installed point-to-point cable ends up looking just like a patch cord, that is, stranded cable with plugs on both ends. But of course, the patch cord is pre-assembled. It's purchased from a manufacturer, tested and warranted, of course, but it's of a fixed length, for example, 15 or 20 feet. However, what that means is if you install that between two devices, you may have slack cabling. Now, sometimes you can accommodate that, of course, if that slack cabling is going to be in an overhead pathway. It can simply be coiled up and stored in place with a hook and loop type of tie. But of course, if you've got a cabling going through conduit, from one panel to another, then you've only got one option, and that is to leave a slack loop of cable underneath the in the enclosure itself, and that can be bad form. It can be not only it takes up space, but may cause some other problems, for example, electromagnetic pickup and things like that. So point-to-point cabling, field installed, is good for those kind of situations.
Good. Here's a question from a well-known manufacturer. Historically, most installations have occurred sometimes haphazardly on the floor. What's the best method to get to a standard network configuration short of a full network audit that might include rip and replace?
Well, again, it goes back to I think to the original design, the idea of the structured cabling standards, the logical progression of that, from the telecommunications room or the micro data center, with common pathways led to zone enclosures, consolidation points, and then well-rated and managed cabling that goes to control panels and endpoints. Yes.
So the standards documents certainly would help.
They absolutely do, and in a way, it's the first point of reference is to look at the standards, because they give you all that guidance for effective routing, pathways, and management.
So, Bob, when you showed the diagram and you showed the riser and the work areas, could you have some progress made by focusing in on maybe those riser areas first?
Yeah, that's a good point, Mike. The riser cables themselves that come from the entrance facility, typically they would be managed in vertical pathways. They might go between floors, for example, in buildings. They would, in each of those floors, there would be a telecommunications room, or more than one possibly. And from the telecommunications room or the micro data center would come cables that would go to the zone enclosure. So the riser is a very good place to start. What you often find is the sprawl occurs in the telecommunication room or the zone enclosures, as some of those horror stories that Mike showed will show us.
Very good. Another question. In structured cable, is structured cable usually always solid copper terminated in jacks, and is P2P, point-to-point cable, always stranded copper with pre-terminated or factory terminated plugs? Well,
it's 99% of the time that is the case. The standards themselves call for the use of solid copper cabling for those structured cabling links, but there are provisions to allow for stranded. And the point is, with the conductor wire gauge being equal, stranded cable has a higher insertion loss or attenuation than solid. And so what that means is that you're not going to be able to support that data communications over the same length to meet the channel performance. So I'll give you an example. If you used a stranded 24 wire gauge cable, your maximum channel length decreases from 100 meters to about 80 meters to support the same data rate with the same performance.
Very good. I would encourage the audience to continue to submit questions, even though we're about 3 minutes to close here. But go ahead and submit questions. If we cannot get to them live, we'll certainly get to them offline. So please take advantage of these resources. Another question, how can I determine if a network is good or bad regarding performance? What are some of the measures involved in measuring a network's performance?
That can come at several levels, because it depends whether it means to take into account the performance of the active equipment, when of course you're concerned with aspects such as bit error rate that relate to then frame error rate. And the issue with bit error rates is, especially in the line of using it with motion control equipment, some of the manufacturers that we're partners with, motion control equipment, if it receives sort of 3 consecutive frame errors, then that industrial equipment will actually shut down. And you can imagine that a motion control situation would do that if it was getting errors and then with different placements of the robotic arm that could be result in inaccurate machining at best, and sort of a severe damage at worst. But going one level down, just looking and focusing on the structured cabling, and there is a test equipment manufactured by a variety of companies. So one comes to mind, such as Fluke, and the test equipment is used to measure the performance of structured cabling, and that information is retained and given to the end user and can be referenced in the future. So it depends on what level, but a variety of tests can be performed. And
just a minute or two more, are the structured cabling and point-to-point cabling solutions you described suitable for PoE, Power over Ethernet?
Oh, yeah, absolutely, yes. The Power over Ethernet, again, the fundamental defining standard was developed by the IEEE, and it comes in various forms. The first standard to be released accommodated power delivered over the twisted pair copper cabling. Of course, it won't be suitable for fiber, but and that delivered up to about 15 watts, and running at about 48 volts. Standard's been enhanced, and now you can get about 25 watts of power, and the standards groups are looking to develop that even higher. Some of the providers of PoE equipment, I think, can deliver up to about 60 watts across twisted pair copper cabling. So absolutely.
Excellent, very good. We'll get to the other questions offline and post a link to where the questions are answered in text so that anybody visiting or revisiting the presentation can get to that. Now that we're just about done, we want to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please, we'd ask you to take a moment to complete it as we use this information to improve our webcasts. On behalf of Control Engineering, CFE Media, and the whole team, thanks for attending the webcast. Thank you to our sponsor. The webcast is copyright 2014 CFE Media. This concludes our webcast for today. Thank you very much for attending.